Hello everyone, today we'll be discussing about number system conversion, and the number system involved are decimal, binary, octal, and hexadecimal. Before we jump into the formal discussion, a quick review about the bases and the characters used for each number systems are shown in your screen. For decimal number system, they use 10 as their base, and the numbers you can use to represent a decimal number ranges from 0 to 9. For binary number system, they have 2 as their base, and the numbers you can use in order to represent a binary number ranges from 0 to 1. For octal number system, they have 8 as their base, and you can use numbers ranging from 0 to 7 in order to represent an octal number. Lastly, for hexadecimal, they have 16 as their base, and you can use numbers 0 to 9 and letters A to F in order to represent a hexadecimal number. The discussion will be divided into 4 parts. For part 1, we will be converting decimal numbers. For part 2, we'll be converting binary numbers. For part 3, we'll be converting octal numbers, and for the last part, we'll be converting hexadecimal numbers. For the first part, we will be converting decimal numbers into binary, octal, and hexadecimal. For the first topic, decimal to binary, I'll be giving 3 examples for each conversion. Example A will be a whole number. Example B will be a fractional part of a number, which means that we will be converting numbers that are located on the right side of the decimal point. And for example C, we will do a combination of a whole number and the fractional part of the number. For example A, we'll be dividing the given to the base of a binary number, which is 2. So 105 divided by 2 will have 52 and the remainder of 1. After that, you'll get the quotient, which is 52, and divide it into 2 again. You'll have 26 with a remainder of 0, and you'll continue the process until you reach a number or a quotient that is less than the base of the binary number. In this case, the last equation is 3 divided by 2, which is equals to 1. 1 is less than 2, so we'll stop right here, and we will consider the final quotient as the most significant bit, or the bit that is located in the leftmost part of a binary number. After you reach the most significant bit, all you have to do is write the remainders from bottom to top. So the answer for the first example is 1101001. That is the binary equivalent of decimal 105. For the next example, 0.25, all we have to do is the opposite of the operation we've used for the first example. The opposite of division is multiplication, so we will multiply the second given to the base of the binary number. So 0.25 multiplied by 2 will have a product of 0.5. Now, on the previous example, we took the remainder. In this example, we will take the whole number part of the product, which in this case is 0. After which, we will take the fractional part and multiply it again to 2. The process will stop once we reach a fractional part that is equals to 0. We'll take 0.5 and multiply it into 2. The answer will be 1.0. Now that the fractional part of the product we have right now is equals to 0, we will stop the process, and all we have to do from this point is to rewrite the whole number part we've taken from the product. The way to write it is opposite to how we did it on the first example. So instead of writing it from bottom to top, we will write from top to bottom. So the binary equivalent of decimal point 25 is equals to 0.01. Now for the last example wherein we're going to convert a combination of whole number and fractional part of a decimal number. All we need to do is do the previous process we've discussed before this example. So for the whole number part, you will be dividing it to 2 and you will take the remainder. For the fractional part, you will be multiplying it by 2 and take the whole number. So as you can see, in this example, the fractional part is non-terminating. Now, what you have to do in case you encounter this example, this type of numbers, you have to look for the repeating fractional part of the product, which in this case is 0.16. So as you can see, when you multiplied 0.58 by 2, which is the second equation, it is the same, or the fractional part is identical to the product of the last equation flashed on your screen. Once you've successfully converted the following, all you have to do is rewrite them properly. So for the whole number part, write it from bottom to top, with the most significant bit being the first bit, of course, and the fractional part from top to bottom. So the binary equivalent of decimal 122.79 is 111010.11001100. For the next topic, we'll be converting decimal numbers to octal. The process is pretty much the same, but the only difference is that we'll be using the base of the octal number system, which is 8. So for the first example, 842, we'll be dividing it by 8. We will take the remainder until we reach the quotient, which is less than the divisor. After the process is done, we will be rewriting it from bottom to top. So the final answer for this, or the octal equivalent of decimal 842, is 1512 octal. For the second example, we will be converting the fractional part of the decimal into octal. So we will be multiplying 0.250 to 8, and the product is 2.0. Since the fractional part of the product is already 0, we will end the process here and we will take the whole number part of the product. So the answer will be octal equivalent of 0.250 is equals to 0.2 octal. For the last example, we will just do the same process as we've done on the previous examples. We will be dividing the whole number part by 8, and we will be multiplying the fractional part by 8. So the octal equivalent of decimal 115.625 is 163.5 octal. For the last topic, in converting decimal numbers, we will be converting decimal numbers to hexadecimal. The process is the same. All you have to do is change the divisor and the multiplier to the base of hexadecimal number system, which is 16. So for the first example, 325, we will be dividing it to 16. So 325 divided by 16 is equals to 20. The remainder is 5. And 20 divided by 16 is 1. The remainder is 4. The last quotient is less than the divisor, so we'll stop right here. And we will take the remainders and rewrite it. The hexadecimal equivalent of decimal 325 is 145 hexadecimal. For the next example, we will be multiplying 0.65 to 16, and the answer will be 10.0. Since the fractional part is already 0, we will stop right here and rewrite the answer. So the hexadecimal equivalent of decimal 0.625 is 0.8 hexadecimal. For the last example, we will be converting 777.77 decimal. We will take first the whole number part and divide it into 16, and take the fractional part and multiply it to 16. The hexadecimal equivalent of decimal 777.77 is equals to 309.C51 EB85 hexadecimal. So for the second part, we will be converting binary numbers to decimal, octal, and hexadecimal. For the first topic, we'll be converting binary numbers to decimal. For the first example, which is a whole binary number, the method we'll be using is called positional notation, and there are steps we can use to easily understand this method. So for the first step, we should know the base of the number we are converting. In this case, we're converting binary numbers, so the base will be 2. That base will be used as the base of our multiplicand, or the number we are going to multiply to the value of the bit in a specific position. Second step is to start from the rightmost part of the whole number. The starting point of the bit we are going to convert for the fractional part is different, so we will be discussing that later on after this example. After that, we will raise the multiplicand to 0, and it increases as we go to the leftmost part of the binary number. In this example, the rightmost bit is raised to 2 raised to 0. The second one will be 2 raised to 1. Third one will be 2 raised to 2. And we will be skipping those with off values, or bits that have 0 as their value. The next bit to it will have a power of 4 since it's on position 4. After that, the last step will be adding the products of the binary numbers. So the answer will be 23. Another method you can use if you are more comfortable with it is lining up the given and writing the equivalent of each bit for each position of the bit, starting from 1, then multiplying it by 2, then multiplying it by 2 again, so that will be 4, and so on and so forth. After which, all you have to do is just take the values of those with on values in the binary number you are converting. So you'll be taking 1, 2, 4, and 16, and that will be equal to 23. So the decimal equivalent of binary 10111 is 23. Now for the second example, we will be converting the fractional part of a binary number. As I've said a while ago, the method we'll be using is the same. They only have two differences. The first difference is that the exponent of the multiplicand here will not be positive, it will be negative. It will not start from 0, instead will start from -1. And the second difference is that instead of starting from the rightmost part, we will start from the leftmost part, the one closest to the decimal point. So in this example, 0.101, the leftmost bit closest to the decimal point will be 2 raised to -1 multiplied by 1. That will be equals to 0.5. And since the next bit is 0, we will be skipping it. We'll proceed to the next bit. The next bit is on the third position, so it will be raised to -3 multiplied by 1. That will be 0.125. We will be adding the products and the result will be 0.625. So the decimal equivalent of binary 0.101 is 0.625. For the third example, we will just do the same thing as we've done on the previous examples. So for the whole number, we will start from the rightmost part and then we'll proceed to the fractional part, starting from the leftmost bit closest to the decimal point and add the product. So as you can see, for the whole number, we have 63, and for the fractional part, we have 0.375. So the decimal equivalent of 111111.0110 binary is 63.375. For the next topic, we'll be converting binary numbers to octal. For the first example, we have a whole binary number, and in order to convert it, first we'll have to group them by 3 bits for each group, starting from the rightmost side to the left. So each group of bit, you'll be using 1 to 4 as the equivalent for each bit respectively, with 1 being the equivalent of the rightmost bit. So the first group here in our example will be 111, and the second group will be 010, and the third group will be 11. Next thing you have to do is add the equivalent of the bits with on values or the ones, ignoring the equivalent of the off values or the bits with zeros in them. So for the first group, 111, since every bit has their values turned on, the answer will be 7. For the second group, 010, since the middle value or the value with a decimal equivalent of 2 is the only bit turned on, the equivalent will be 2, of course. And the third group, which is 11, their values are turned on and their decimal equivalent will be 3. The answer or the octal equivalent of binary 11010111 is 327 octal. So for the next example, the fractional part of the binary number, we will group the given into 3 groups, same as what we did on the first example. The only difference is that we will be grouping the bits from starting from the leftmost part, the one closest to the decimal point, up to the right side. Also, the values we'll be using is reversed. We'll start with 4, then 2, and then 1. On our previous example, we used 1, 2, 4 respectively from right to left. This time I'll use 4, 2, 1 respectively from left to right. So for the first group, we have 110. Second group, we have 011. And third group, we have 11. So for the first group, since the first 2 bits are turned on, the equivalent will be 6. The second group, since the last 2 values are turned on, its equivalent will be 3. And the last group, since the first 2 bits are turned on, the value will be the same as the first group. So it will be 6. And the answer for this given, the octal equivalent of binary 0.11001111 is 0.636 octal. For the third example, all we have to do is combine the process we did on the previous examples. So for the whole number part of the binary number, we'll be grouping them by 3 bits for each group, starting from the rightmost part to the left. And for the fractional part, we will be also grouping them by 3 bits for each group, starting from the leftmost part, the one closest to the decimal point, up to the right. We'll be using 1 to 4 from right to left for the whole number part, and 4 to 1 for the fractional part, starting from left to the rightmost part. So for the whole number part, the equivalent will be 52, and for the fractional part, the equivalent will be 0.26. So the octal equivalent of binary 101010.01011 is 52.26 octal. Now you might be wondering, why are we using 4 to 1 and 1 to 4 for converting binary numbers into octal? As we've mentioned a while ago before we proceeded with the conversion, the maximum character or number we can use in an octal number system is equals to 7. So if you turn on all the values in a binary number grouped to 3, the maximum number you can have is 7. So for the last topic, for this part, we will be converting binary numbers to hexadecimal. The process is the same. We'll be grouping the given binary, but this time into 4 bits. We will be using 1248 and 8421 as the equivalent of the bits with on values. We will be using 8421 because the maximum character you can use in a hexadecimal number system is F, and the decimal equivalent of F is 15. So for the first given, we have binary 110111101. We will be grouping them into 4 bits for each group, starting from the rightmost side to the left. So for the first group, we have 1101. For the second group, we have 1011. And for the last group, we have 1. So we will be using 1248 from right to left. And the equivalent of the first group is 13. And the second group is 11. And the last group is 1. So 13, its hexadecimal equivalent will be D, and 11, its hexadecimal equivalent is B. For 1, it stays as it is. The hexadecimal equivalent of binary 110111101 is 1BD hexadecimal. For the next example, we will be converting the fractional part of the binary number. We will be grouping them into 4, starting from the leftmost side to the right. So we'll have for the first group 110, and for the last group we have 1. We'll be using 8421 as the equivalent of the bits with on values. So for the first group, we have 14, and the next group we have 8. So the hexadecimal equivalent of 14 is E, and hexadecimal equivalent of 8 still 8. The hexadecimal equivalent of binary 0.11101 is 0.E8 hexadecimal. Now for the last example, we will just do the same process as what we did on the previous examples. So for the whole number part 10111, we'll be grouping them into 4 bits, starting from the rightmost side to the left and using the 1248 equivalent for each bit with on values. And for the fractional part, we will be grouping them by 4 bits as well, starting from the leftmost side to the right, and we'll be using 8421 as the equivalent of the bits with on values. So for the whole number part, its equivalent is 17, and for the fractional part, the equivalent is 0.34. The hexadecimal equivalent of binary 1011.001101 is 17.34 hexadecimal. For the third part, we will be converting octal numbers to decimal, binary, and hexadecimal. For the first topic, we will be converting octal numbers to decimal. The process is the same as how we convert binary numbers to decimal. The only difference is that instead of using the base of a binary number, we will be using the base of an octal number, which is 8. So for the first example, 124 octal, we will start with the ones digit, which is 4. We will multiply it by 8 raised to 0. The answer will be 4. For the next digit, which is 2, we will multiply it by 8 raised to 1. That will be 16. And for the last digit, we will multiply it by 8 raised to 2. And the answer will be 64. So we will add the products and we will have a sum of 84. The decimal equivalent of 124 octal is 84. For the second example, 0.27 octal, we will start from the 10th digit, which is 2, and multiply it by 8 raised to negative 1. The answer is 0.5. For the next digit, which is 7, we will multiply it by 8 raised to negative 2, and the answer is 0.125. We will add the products, and the sum is 0.625. So, the decimal equivalent of 0.27 is 0.625. For the next example, we will just combine the process we did from the previous examples. For the whole number, 561, we will start with the ones digit, and for the fractional part, we will start with the tens digit. The decimal equivalent of 561 octal is 369, and the decimal equivalent of 0.35 octal is 0.453125. So combine the answers, and so the decimal equivalent of octal 561.35 is 369.453125. For the next topic, we'll be converting octal numbers to binary. So for the first example, we have 250 octal. In order to convert an octal number to binary, all you have to do is represent each digit with 3 bits having a value of 1 to 4 respectively from right to left. So as you can see, 0 is 000, 5 is 101, and 2 is 010. So the binary equivalent of 250 octal is 10101000. For the next example, the fractional part, still the same. Each digit will be represented by 3 bit, but you will be using 4 to 1 respectively from left to right. So as you can see in our example, octal 0.752, 7 is the largest possible number in an octal number system. So all of the values are turned on. So we have 111, 5 is 101, and 2 is 010. So the binary equivalent of octal 0.752 is 0.11110110. For the next example, we will just combine the process we did on the previous examples. So for the whole number part, 641, we will be using 1 to 4 from right to left. And for the fractional part, we will be using 4 to 1 from left to right. So the binary equivalent of 641.37 octal is 11010001.011111. So for the next topic, we will be converting octal numbers to hexadecimal. There are two parts in converting an octal number to a hexadecimal number. The first part is you'll have to convert the octal number to binary. And you will be converting the binary equivalent of the octal to get the hexadecimal equivalent of it. So for a whole octal number, our first example, 33 octal, the binary equivalent of 33 octal is 11011. The binary number, we will take that and convert it into hexadecimal. The hexadecimal equivalent of 11011 is 1B. So the answer for example A, the hexadecimal equivalent of 33 octal is 1B hexadecimal. For the next example, we will do the same thing. We will first convert the given 0.347 octal to binary. So the binary equivalent of it is 0.011100111. We will take the binary equivalent of that octal and we will convert it into hexadecimal. So the hexadecimal equivalent of 0.011100111 is 738. So the answer for this example is the hexadecimal equivalent of 0.347 octal is 0.738 hexadecimal. For the last example, we will just combine the process we did on the previous examples. For the whole number and the fractional part of the number, we will first convert it into binary, and the binary equivalent of that octal, we will be converting it again to hexadecimal. So for this example, the hexadecimal equivalent of 27.165 octal is 17.788 hexadecimal. For the last part, we will be converting hexadecimal numbers to decimal, binary, and octal. For the first topic, we will be converting hexadecimal to decimal. As usual, it is still the same as how we convert binary numbers to decimal. The only difference is that we'll be using the base of a hexadecimal number, which is 16. So we will start with the ones digit. So 16 raised to 0 times 8 is equals to 8. 16 raised to 1 times 9 is equals to 160. And 16 raised to 2 times 10 is equals to 2560. So the next step is to add the products, and you'll have the sum of 2712. So the decimal equivalent of A98 hexadecimal is 2712. For the next example, we will start with the tenths digit, which is 4. 16 raised to negative 1 times 4 is 0.25. And for the next digit, 16 raised to negative 2 times 15, which is the decimal equivalent of f, that will be equals to 0.0585935. Add the products and you'll have a sum of 0.30859375. So the decimal equivalent of 0.4f hexadecimal is 0.30859375. For the next example, we'll just have to combine the process we did on the previous examples. So for the whole number 1AB, we'll start with the ones digit, and for the fractional part, we'll start with the tenths digit. The decimal equivalent of the whole hexadecimal number 1AB is equals to 427, and the decimal equivalent of the fractional part of the hexadecimal number point D2 is 0.82033125. You combine the answers, and the decimal equivalent of 1AB point D2 hexadecimal is 427.8203125. For the next topic, we'll be converting hexadecimal numbers to binary. It's the same as how we convert octal numbers to binary. The only difference is that each digit will be represented by 4 bits, and we'll be using 1, 2, 4, 8 from right to left as the value of each bit respectively. So for the first example, CA89, equivalent of 9 is 1001, 8 is 1000, A, which is 10 in decimal number system, it will be represented 1010 in binary. C is 12 in decimal number system, so for binary system, it will be 1100. So the final answer, the binary equivalent of CA89 hexadecimal is 1100101010001001. For the next example, we will still represent each digit with 4 bits, but we will use a different equivalents for each bit. We will have 8, 4, 2, 1 respectively from left to right. So for the first digit, 8, we will have 1000 as its binary equivalent. We have A, which is 10 in decimal number system. It will be converted as 1010 in binary. And 3, that will be 0011 in binary. So the answer for this example, the binary equivalent of 0.8A3 hexadecimal is 0.100010100011. For the next example, we'll just have to combine the previous processes we did. So for the whole number part of the hexadecimal number, we'll group it into 4, and we will use the equivalent for each bit 1, 2, 4, 8 respectively from right to left. And for the fractional part of the hexadecimal number, we will use the equivalent 84214 for each bit starting from the left side to the right. So the binary equivalent of 7B.8A hexadecimal is 11111011.10001010. So for the last topic, we will be converting hexadecimal numbers to octal. So it will be divided into 2 parts. For the first part, we will convert the hexadecimal number to a binary number, and we will take the binary equivalent of that hexadecimal and convert it into octal. So for the first example, 984 hexadecimal, the binary equivalent of it is 1001 1000 0100. We will convert it into octal, and the octal equivalent of this binary is 4604. So, the octal equivalent of 984 hexadecimal is 4604 octal. For the next example, we will be converting a fractional part of a hexadecimal number. The process is still the same. So the binary equivalent of 0.C4b is 1100 0100 1011. We will take the binary and convert it into octal. So the octal equivalent of 0.C4b hexadecimal is 0.6113 octal. For the last example, we'll just have to combine the previous process we did in the last two examples. So for the whole number part as well as the fractional part of the hexadecimal number, we have to first convert it into binary, and we will take the binary and convert it into octal. So the octal equivalent of AD.7F hexadecimal is 255.376 octal. So that is all. If you have questions, please don't hesitate to ask them on the comment section below for it to be addressed properly. If some of the examples are quite confusing, please do leave a comment so we can clarify things out. Thank you.